Okay, so what's going to happen now on is we have about 3 lessons. First is lesson 10, which is on stability and controllability. Next is lesson 11, which talks about the low level control and controller. And lesson number 12, which talks about the path planning and going from waypoint navigation. So let me tell you, you are going to see a lot of equations. And this material, if you decide to just read it, is super duper boring. But this material is very important from implementation point of view. So unless we understand what these equations are, unless we implement those equations and program those equations inside Mambo, some of this stuff will not make sense. So this class onwards, what we are going to do is I'm going to talk about the equations. Some of these equations are the same equations that you have seen in Coursera course. You have seen these equations when we did the dynamic simulation. But what we are going to do is we are going to start with the first line approximation and gradually step by step build, and finally we are going to fly the Mambo with our own flight control. And at the end of the day, at the end of the semester, you would realize that writing a flight control software is not super duper difficult if you understand the fundamental principles involved in writing a simple code on the flight code. So far, we talked about the state estimation and why is state estimation needed. The state estimation is needed because please understand, we have an IMU. That IMU has 3 accelerometers and 3 gyroscopes. So that IMU has 3 accelerometers and 3 gyroscopes. And from these, somehow we want to find out the roll, pitch, and yaw. So we want to find out the roll, pitch, and yaw. And we need to stabilize the quadcopter using some type of control algorithm. We also have optical flow. We also have barometer. Barometer would help us maintain the altitude. Optical flow will give us X and Y translations. So with all these sensors, the data that is coming to us is noisy. So we want to find out or fuse this data to find the the best possible estimate of the quantities that we want to be measured. And then what we want to do is we want to design some sort of controller that stabilizes the quadcopter. So what we are going to do is, let me kind of tell you what's going to happen next. In today's lesson, we will talk about a little bit about the theory of stability. And then what we will do is we will look at a very simple approximation of the dynamical equations. And then we will see how to program those equations in something called as the flight code. And then what we would do is we will flash this flight code onto our Mambo. We'll flash this flight code onto our Mambo and see if the Mambo is working the way we want it to work or not. We are gonna go in a step-by-step fashion. So first and foremost, we are gonna look at attitude stabilization. So attitude stabilization. What do I mean by attitude stabilization? Attitude stabilization means if our quadcopter is flat, it should stay flat. If there is a roll or if there is a pitch, the controller should bring it back to its level position. And we are gonna do it in a very step-by-step fashion. And I will tell you exactly how it needs to be done. So what you should do is, and if you can bring your Mambos in class, I would encourage you to bring your Mambos in class. So what I want you to do is, I want you to basically tie a small string that is going from the center of the Mambo. So basically this Mambo should be held on a string. Are you with me? So it should become like a pendulum. So when you next time when you come in class, what I want you to do is, so if you come to class, this is the Mambo. You can see in the Mambo there is this notch. Okay. So what you can do is you can put a small pin or small piece of maybe a toothpick or something from here, add the string and basically make it into a pendulum. And what we want to do is we want to make sure that Mambo can sustain the level flight. So this is Mambo's X. This is Mambo's Y. So our next assignment is going to be, and I'll tell you, this is what is going to be the next assignment. We will have this Mambo on a pendulum. So if I rotate Mambo like this, you should observe that these two props should speed up and these two props should speed down, and then basically they should stabilize the Mambo around x-axis. If I lift the Mambo up, if I pitch it up, then these two props should slow down, these two props should speed up, and then Mambo should kind of stabilize. You don't have to run the Mambo at full speed. What you want to do is you want to create a Mambo in some sort of a pendulum and then make sure that it has the pitch stability, it has the roll stability. Everyone understood this? Now the question is, how would you ensure the pitch angle? Your pitch angle would be calculated from your complementary filter. The roll angle will be calculated from your complementary filter. We are at this point for the next assignment, for the next task, we are not going to worry about yaw. We'll deal with yaw a little bit later. But for the next task, next assignment, we want to ensure that if Mambo is a pendulum, if you disturb the Mambo in roll and pitch simultaneously, it somehow should be finally be able to stabilize. And then we would tune the gain so that the Mambo is stabilizing itself. Mambo is stabilizing itself as a pendulum. And once you have the robust performance, which means you have tuned your gains very well, then you can take that string off and have the props fly at full speed, and you will see that your Mambo will hover at this. Basically, it will hover for maybe 5 to 10 seconds, and then it will crash. and then we would do the altitude stabilization. So next first step is attitude stabilization, roll and pitch. Then we are gonna stabilize the barometer stabilization. How would we do the barometer loop? For if you want to maintain the barometer, all these props, if the height is low, should speed up. If the height is high, then speed down. Are you with me? So we would actually write those loops inside the MATLAB and then burn it on the in the motor mixing algorithm, and then we'll flash it onto Mambo, and we'll see if you are able to achieve the stable hover. That is always the first step, stable hover. And after we are done with stable hover, assuming we get to stable hover, then what we would do is we will get the data for X and Y from the optical flow, and then we will try to get Mambo moving forward or backward, again using the same PID type control. So basically, if you want your Mambo to go forward, what's going to happen is these two props, basically you will do the differential speeding. I'll give you the matrix for forward, I will give you the matrix for left, right, and then we have the motor mixing algorithm. So at the end, what you should do is you should be able to have your Mambo flying with your flight code. So that's going to happen. So before we do that, it is absolutely critical that you should have your complementary filters working. My online students, any questions? So okay, Alex Sports got it all working. Good job, Alex. Okay, so that means I don't have to give you the solution because one student got it working, so everyone can get it working. Very good, Alex. If you want to show it a little bit later, if you are willing to show it, just show it to everyone. Yeah, its timing delay block was incorrectly configured. Correct. Very good. Okay, so once again, word of caution. The material that we are going to see is mathematically intense, but don't let that math scare you. I'm trying to give you the meaning behind those equations, and that meaning, that physics, is super duper important. All right, first and foremost question, and we discussed this. What do I mean by stability? What do I mean by what is the concept of stability? Yeah, no, go ahead. You're saying something? Stability?
Yeah, so basically that all your outputs tend exponentially towards each other.
Okay, correct. So there are three types of stabilities. So one thing is simple stability. What do I mean by simple stability? Or also called as the neutral stability, which is like the ball rolling on a flat surface. So if you push it, it goes to the other location but stays there. So this is called as simply stable. The next one is asymptotic stability, which means what you have is it's sort of a ball. This ball kind of rolls and finally gets down to the position of least potential energy. So this is called as asymptotic stable. And the last but not least is unstable. So basically this is unstable. And in robotics 1, I kind of talked about the eigenvalues. Remember eigenvalues I talked about in robotics 1? Can someone tell me how are eigenvalues related to stability? Do you remember eigenvalues? We talked about it. Real part of eigenvalues is 0. Real part of eigenvalues is less than 0. And real part of eigenvalues is greater than 0. And this is something I discussed in that class, but I will try it again. So x dot is equal to ax. A is a number which is like 5, 6, 7, 8. So x is equal to say 3x. X dot is equal to 3x, which is dx by dt is equal to ax. Dx over x is equal to a dt. Integrating both sides, I have ln of x is equal to at plus c, which means x of t is equal to e to the power at plus c. T is an independent variable, which means what I can do is I can plot t on x-axis and I can plot x on y-axis. Since e to c is a constant, x of t can be written as a e to the at. Are you with me so far? Do you remember we did something like this in robotics 1? Yes, no? What? Oh, it was long time ago. So if my a is equal to 0, what happens? If my a is equal to 0, this is capital A. This is a is equal to 0. Do you agree with me? X of t is going to remain a all the time. Are you with me? As time goes from 0 to infinity, x is going to remain capital A. That means the system is not going anywhere. Now, if my a is less than 0, do you agree with me? It's kind of going down, which means as time t goes to infinity, x of t goes to 0. Do you agree with me? If my a is greater than 0, so this is a less than 0. If my a is greater than 0, it's going to increase exponentially. So this is a greater than 0. So I have a less than 0, a greater than 0. Please note a is a scalar. If my a is a matrix, then eigenvalues dictate the stability. So if my real part of my eigenvalues is equal to 0, system is simply stable. If the real part of the eigenvalues is less than 0, system is asymptotically stable. If the eigenvalues real part is greater than 0, then the system is unstable. Everyone understood this? Now, this is the concept of stability that is discussed. So you can see that this ball can roll inside, can roll and become unstable outside. And if it is rolling on a flat surface, it's actually neutrally stable or simply stable. Now, this equation may look a little bit confusing, but it is saying the same thing. Only unfortunate part here is that it is talking about in the language of mathematicians. And unfortunately, next few slides would talk about the concept of stability from mathematics point of view. And I would explain it to you what it means. Stability is always defined with respect to something. You cannot define arbitrary stability. So for an example, the stability could be with respect to a fixed point, or stability could be with respect to a particular solution. Now, what do I mean by that? A classic example is we have this mambo. When this mambo is flying in a stable equilibrium like this, it is stable about certain point. And what is that point? That is the point when the horizontal velocity is 0, vertical velocity is 0, and basically the roll rate, pitch rate, and yaw rates are 0. Everyone understood this? In other words, all the velocity terms are 0. That is called as equilibrium point. Equilibrium point is when all the derivatives are equal to 0, and that is also called as equilibrium state. So equilibrium state means all derivatives is equal to 0. Now let me give you a very simple example. The example is force is equal to mass times acceleration. This is the equation that is used in dynamics. Acceleration is the derivative of velocity. So m v dot. If my velocity is 0, if my v dot is equal to 0, that means I am in the state of equilibrium. So where would you see the state of equilibrium? So let me give you a simple example. A spring balance. You have a spring balance and you add some weight. So what happens is the spring is stretched, and then weight of the mass m times g is equal to k times deflection of the spring, k delta. And at that point, this mass is considered to be in equilibrium. So this 0 is the equilibrium state. Sometimes what you want is you want to study the stability about a particular solution. What do I mean by particular solution? Here is a classic example. You program the mambo to go in a straight line, maybe a line follower, and this mambo is traveling in the straight line. All of a sudden, there is a gust, and this mambo kind of goes towards left or towards right. But the stability about solution means even though this mambo gets displaced from its desired path, it actually goes back to its original path and continues to follow the path. So stability about fixed point is mambo is flying in a level flight, just stationary. If you push it, you pull it, move it left, move it right, it goes back and stays steady. This is called stability about the equilibrium point, and that we will achieve first. So in the assignment, once you do the complementary filter, and I will tell you the loops that you need to implement, that will be used to achieve the stability about equilibrium. Everyone understood this? Once we achieve the stability about equilibrium, and that stability shouldn't just be simple stability, it has to be asymptotic stability, which means if your mambo is flying at this position, if you displace it, it should go up, come down, go up, go down. It should become like a pendulum and settle down to its original position. If I were to push this mambo left, then it should go back and come down and stay at the initial X position. If I push Mambo towards Y, it should say go forward, backward, and finally it should go to its original position. That is called as equilibrium. That is equilibrium about the fixed point. Everyone understood this? So the task in next 2 weeks is to achieve equilibrium about the fixed point for Mambo. Everyone understood this? Once we are successful, then we will achieve the equilibrium about a solution. In other words, if our Mambo, what we would do is we'll actually program the Mambo to go straight. And as Mambo is going straight, if you were to deflect it, it should come back and follow the straight path. It should not. Let me tell you. So let me explain it to you how the stability would work around a solution. What is our solution? Path following. Do you agree with me? This is my solution. If I have neutral stability about path following, I push the Mambo goes here and it follows the path. So there is a constant X offset that Mambo would continue to travel. Everyone understood this? That is the neutral stability about the path or about the solution. But what we want to achieve is we want to achieve the asymptotic stability, which means this Mambo is following, we push, Mambo comes back and goes back and then still continues to follow the initial path. Everyone understood this? And it's not difficult. Once I explain you, there are some, once I explain you the loops that we are gonna program in, you will know that this programming a flight control system is very straightforward. Online students, everyone understood this? So there is equilibrium about fixed point. There is equilibrium about a solution. There is also a thing called as equilibrium about the periodic solution. Now, what is that? If I program Mambo to follow a circular path, if I program Mambo to follow a circular path, do you agree with me? This is a periodic solution, which means after some time, Mambo is going to come back to the position it started. Do you agree with me? This is a periodic solution. I don't think we'll get there, but if you can get there, that's fantastic. Basically, you will program x square plus y square is equal to r type of code in your path following. So basically your path, rather than a straight line, is going to be a circle. And this is the periodic solution. And what's going to happen is, if you displace Mambo while it is traveling in circle, it should still go back, but it should still follow the circle. Everyone understood this? That is what it is. Circular path following, you will have to implement some type of a heading control, which means you need to implement a controlled yaw. That is more complicated. But I think at least level flight and straight flight, we should be able to do. Okay, next part. There was a very, very famous scientist called Lyapunov. He defined the concept of stability. And the concept of stability that he defined is in terms of mathematical notations and set theory. But before I explain you the definitions, I want you to think about a very simple example. As a kid, I used to play on swing. Have you played on swing as a kid? Have you tried something called as pumping the swing, which means basically there are two ways to pump the swing. So you have a child, small child on the swing, you stand behind and you push him every time that swing comes to you. Do you agree with me? What is happening there? Every time the swing is coming to you, you are pumping energy into the swing. Do you agree? In other words, the baseline energy of the swing is increasing. What happens if the energy starts increasing? The system becomes unstable. Do you agree with me? If the energy starts increasing, you would notice that the swing oscillations, the amplitude will continue to increase because it has more energy. It can do more work. Second thing, if the swing is coming to you and you try to grab it, you try to break it, which means you are taking energy out from the swing. So you agree with me, after some time, the amplitude of the swing dies down and swing stops. What it means, if you have energy, if you think about a dynamical system, or if you think about the equation, and you think about that equation, not a mathematical expression, but something like which has energy. And as time goes on, if that energy increases, I know for the fact that that system or that set of equation is going to behave in an unstable fashion. If I know that energy of that system goes down over the period of time, the system eventually would lose all the energy and basically come to rest. Do you agree with me? Think about it like this. You drink a shot or a caffeine shot and you get energy, maybe 5-hour energy. After some time, all that energy is gone and you feel tired. So you have energy, but if you think about it, if that energy is neither increasing nor decreasing, you agree with me, that swing or that mechanical equation or mechanical system or mathematical system of equation will continue to sustain motion. Everyone understood this? So that is the fundamental concept of Lyapunov stability. So what did Lyapunov say? Is Lyapunov said that I'm going to define a function, and that will be something called as the energy function. And I'm going to observe if that energy function is increasing over the period of time, staying constant over the period of time, or decreasing over the period of time. If that energy function is becoming bigger and bigger and bigger as time goes on, that means the system is unstable, bigger. If that energy function is neither increasing nor decreasing, then it's going to remain stable. If the energy is going to drop down, then the system is going to become asymptotically stable. Everyone understood this? These are the mathematical definitions of stability, instability, and unstable system. Okay. Do you want me to explain these notations or physics is good enough?
What's the difference between exponential and asymptotic?
Oh, exponential stable means drop is sudden. Asymptotic stable means something like this. So that is what is, so you will notice that there is this e to the minus lambda t, that is the limit. So it's like, anyone interested in understanding the notations, or everyone understood the physics? So what this notation means, if for all r that belong to capital R, which is the set, such that R remaining within the small capital R set, x of 0, which is the initial point, is less than certain value, then x of t, the time evolution, remains always less than capital R when time t is within R. Okay. What does it mean in human language? This is what it means. Yeah, mathematicians unfortunately have a complicated way of saying simple things. So this is what it means. This capital R, this capital R means real. And real means not imaginary, not negative. So it's not like square root of minus I or minus 3I or a square root of minus 1. So these are all real numbers. Real numbers means 0, 1, 2, 3, 4. That's what it means. So there are three things that we are considering. First is x is equal to 0. Second thing is as x, time is going forward, and this is time. So what this definition is saying is, if you start at some location x of 0, this is x of 0, as time goes on, as long as you stay below this bound, the system is stable. So this is capital R, this is small r, this is time, and this is x of t. Are you with me? That is all that equation means. But what I have done is I have taken the slice of the equation. So if you were to see the cylinder, the very first cylinder, if you take the slice of the cylinder, you are going to see something like this. No matter what happens, the x value will always be less than a real threshold value. That it means by stability. So that is something called as the Lyapunov stability. And now let's revise, look at this equation again. And this, so if you take some advanced courses, you will see all these terms. So this means for all values of R, for all real values 0, 1, 2, 3, 4, 5, for all values which are belonging to the real set, such that small r belonging to the real set, where x of 0 initially, if it is starting at R, and for all time it is staying below R, then it is going to be in stable state. Everyone understood this? If you start small, it will stay small. It will not go out of the bounds. That is the Lyapunov definition of stability. Now, what happens in the case of asymptotic stability? In asymptotic stability, what this means is that time goes on, x of t goes to 0. Have you seen in the first case, x of t is less than some bound. In second case, x of t is going to 0. That is what is the asymptotic stability. So this is asymptotic stability. And exponential stability means you have sort of a stricter bound. So you want it to drop exponentially. Everyone understood this? Online students? Now here comes the application. Now these equations that we are going to see, they are super important from implementation point of view. So remember, when we studied the dynamics, we actually looked at these equations. So these are the altitude dynamics equation. Remember the dynamics equation, 12 equations that we talked about? Out of these are the last 6 equations. In last 6 equations, you have an equation which is capital theta dot is equal to omega, and you have another equation which is omega dot is equal to j inverse tau, and you have one term which is body rate, which is multiplied by j omega plus g. That term is usually small. So what I want you to understand is, for a moment, I want you to look at this equation very, very carefully. And remember that we have seen this equation before. Are you with me so far or no? Remember when we looked at the dynamics of quadcopter, we actually simulated this equation using the MATLAB code, Simulink file, and we actually found out, we designed the KP, KI, and KD controller for quadcopter. So those were the exact same equations. The only thing is, there was this additional term. This additional term is the cross product term, which is omega cross j omega plus GA. That term for small quadcopters is ignored. So what we are left with is, we are left with this equation, which is capital theta dot omega b, and omega dot is equal to j tau. And this equation is going to be useful to design the attitude controller. But before I actually tell you what this equation physically means, does this equation look familiar to you or no? All right. Huh? This is not Jacobian. This is the mass matrix, a mass moment of inertia. Okay. So I will explain you what this equation is. So imagine, I will show it. I'll show it to you for the. Let me show it to you for the plus configuration, and then I'll show it to you for the X configuration. So imagine that you have a quadcopter in plus configuration. And you start, this is, remember there is northeast down plane, and basically this quadcopter is flying in a level flight. I'm going to assume that north, east, and down are aligned with the north, east, down of the inertial frame. North, east, down. This is the inertial frame. This is fixed. This north, this east, and this down. And what that means, this is my X, this is my Y, and this is my Z. So that is aligned with the inertial north, east, and down. There are two rates. One is the body rate, which is omega b, and there is inertial rate, which is capital theta, inertial rate. I'm going to write this down as pitch rate, roll rate, and yaw rate. So pitch rate, so this is X, Y, and Z. This is a special case wherein the north is down, X, Y, and Z of the quadcopter is aligned with X, Y, and Z of the inertial frame. Do you agree with me? So what is the rotation about X? Rotation about X is roll. So this is phi dot. No, this has to be in this direction. This is about phi dot. This is about theta dot. And this is about psi dot. Now, what is the rotation about in the body frame, and this is actually super duper important, so please pay attention. Okay, so this is omega x, this is omega y, and this is omega z. Are you with me so far? Now, if I want to write down, can you see that these two coordinate frames, this is super duper important, and I will repeat this once again. This is extremely important from the controller design point of view. My coordinate frames are aligned, which means I don't have to use any transformation in between. Do you agree with me? So can I say something like this? I can say my theta dot, my phi dot, my psi dot is equal to theta dot is about omega y, omega x, and omega z. Are you with me so far? Because the coordinate frames are aligned. This case is not true if that aircraft coordinate frame is not aligned with inertial coordinate frame. And for most general case, it will not be aligned. But we are assuming for the hover controller, for the simple hover controller, my northeast down frame is coinciding with the northeast down frame of the aircraft. Everyone understood this? That is this equation. Everyone understood this equation? Now the second equation is simple. T, which is the torque, is equal to I times alpha. Torque is equal to I times alpha. What are alphas? So torque, do you agree with me? This equation, torque you cannot apply. There is no torque about the inertial frame. So there is no point in doing that, but I can do torque about this. So I can say, and this is very important, I inverse multiplied by torque is equal to alpha. Do you agree with me? And what is alpha? Alpha is nothing but omega dot. Now I actually wrote it slightly differently. So I would just write this like omega y, omega x, omega z dot dot dot. I would have this J inverse. I is actually J inverse, and I'm going to have this torque in Y direction, torque in X direction, and torque in Z direction. Everyone understood this? Now, I also told you one more thing, that if J, mass moment of inertia, is about the center of gravity or the centroid, then this mass moment of inertia matrix is going to become a diagonal matrix. So off diagonal terms are going to be zero. Do you agree with me? So what it means, and this is the crux, what this means is my equation for flight dynamics is going to be super simple. So before I write that equation down and before we write the loops, I just want you to understand. We are considering the case when the aircraft northeast down is aligned with inertial northeast down. So do you agree with me? So what that means is the roll rate, pitch rate, and yaw rate. Roll rate, pitch rate, and yaw rate are nothing but body angular velocities. Do you agree with me? And you have gyros and accelerometers to measure body angular velocities. You can measure those using complementary filter. So basically, the first part of that equation we can get from the sensors. Now, what is happening in the second part? Second part is based on the body angular velocity. I have the derivative and I know the inertia properties. So I can find out the values of torque that need to be applied. In other words, by designing a suitable controller, I can actually stabilize this whole dynamics. Everyone understood this? Yeah, it's not easy in the so let's try to understand. What do I need for stability? Stability means all the derivatives, they have to be zero. Do you agree with me? So somehow what I need to do is I need to make theta dot, phi dot, everything to be zero. Theta dot is zero, phi dot is zero, which means what is theta? Theta is going to be constant. What is phi? Phi is going to be constant. So how would I implement this using a simple controller loop? What I will do is I will design either a proportional controller or a PID or derivative controller or proportional, integral or derivative controller, so that at the end my theta dot, phi dot, psi dot go to zero. Do you agree with me? That is all that you need to do for the hover controller. Now, how would you put this math or whatever we have discussed on an airframe like Mambo? This is where the loops come in. So everyone understood? Here is what I'm going to do. Insert. So this is how we are going to design the flight control system for hover control. So altitude control. What do we want to do in attitude control? My purpose in attitude control is my phi dot should go to zero. My theta dot should go to zero. And I'm going to specify one more thing. I'm going to say my theta and my phi, both of them go to zero. Do you agree with me? If my theta and phi go to zero and stay at zero, my theta dot and phi dot, they are going to go to zero. Everyone understood this logic? I would explain this once again. So what I'm going to do attitude control, I want my theta dot to go to zero and I want my phi dot to go to zero. So for Mambo, and I want you to try this, and I will explain it to you in just few minutes using the code. Last time we had this sensor block. From the sensor block, what we did is we got the acceleration data. And this is the block diagram. From acceleration data, we got an angle. So this is where we are getting, so maybe theta. Then what we did, we got the gyro block. You multiplied that gyro block by a time constant, and then you got theta gyro. You combine these two and you got theta estimate. Now what I want to do is I want to design an algorithm. So controller algorithm to find out theta E, and I want this theta E to go to 0. Everyone understood this? So I want to design some type of controller algorithm so that theta E goes to 0. So how would I find that out? Step 1, find current theta E. Step 2, what is our set point? What do we want this theta E to be? If I want to have pitch control, so if the aircraft is in level flight, what is the value of theta? 0. Do you agree with me? If my aircraft is going like this or my mambo is like this, theta E is non-zero. So what is the error? Error is the actual value of theta minus 0. Do you agree with me? Because 0 is my set point. I want it to be 0. If it is not 0, that's an error. Do you agree? Okay. So what I have is error is equal to theta E minus 0. So which is E. Step 3, if I want to design the proportional control, let me show it to you for the plus configuration. So we are looking at pitch. So pitch means this is X. Yeah, initially it may be a little bit difficult, but you'll get it. I'm pretty confident. This is X, this is Y. So for pitch control, I need to control motor 1 and motor 2. So this is my motor 1 and this is my motor 2. Do you agree with me? So if I want to control, actually no, this is pitch, right? So X, this is Y. I made a mistake. So this is X north, this is Y. And pitch is about, yeah, pitch is about Y. So basically X, so 1, speed of motor 1 should go up, speed of motor 2 should go down. So what I'm going to do is I'm going to set up an algorithm, something like this. So I'm going to say delta omega, this is very important, delta omega is equal to Kp times E. And step 4, omega 1 is equal to omega 1 plus delta omega. Omega 2 is equal to omega 2 minus delta omega. Are you with me? That is the pitch stabilization inner loop. And why is it called inner loop? Because please understand, controller algorithm will continue to do this till theta E is equal to 0. Till theta E is equal to 0, go to step 1. So this is what would be the loop would look like. If theta E is not 0, step 1, find current theta E. Step 2, find error. Step 3, proportional to error, increase the speed of one motor and decrease the speed of another motor. Everyone understood this? Simple, right? I'm going to repeat this once again. It will become complicated. Right.
Okay.
So step number, so this is called as the innermost control loop for pitch stabilization. So till pitch is 0, which means till theta E is 0, find current value of theta E. And how would you find current value of theta E? How would you find current value of theta E? From complementary filter. Why can't you use just accelerometer? Actually, as a matter of fact, for initial test, you can just do it with accelerometer. But if it's a highly maneuvering target, then the accelerometer will not give you good results. You can do it with accelerometer. So for balancing bots, they use accelerometers but then you will have to use the complementary filter. You will find theta E from the complementary filter. Theta E minus 0 is going to give you error. You would have a constant Kp. That Kp will tell you the amount by which speed of one motor should increase and speed of other motor should decrease. Everyone understood this? Now I want you to apply the same logic, and let me ask you this very important question. Wake up, wake up, wake up, wake up. So now my question is, if I have positive pitch disturbance, would this work? So which means if it is pitching up, would it work?
Yes.
If it is pitching down, would it work?
Yes.
Yes. Can you use the same argument or same logic for roll?
Yes.
You can. And that is going to be your assignment. So next Thursday, I would like to see your Mambo pendulum. So what we are going to do? So basically, okay, for Mambo, it's going to be different. Now, what is the difference between the configuration that I have shown here and Mambo? For Mambo, if you want to stabilize the pitch, you have to increase the speed of 2 props and decrease the speed of 2 props. Are you with me so far? In plus configuration, you can just do it with 1. But for Mambo, what you need to do is you need to do with 2 props. Algorithm remains the same. So essentially, what you are going to do is you are going to say, I will actually draw the X configuration. So now this is your Mambo configuration. And I'm assuming, okay, I'm assuming this is M1, M2, M3, M4. So what you will do is you will increase. Can someone tell me the algorithm real quick? If and my north is down are like this. This is my Y. This is my X. So if I want X stabilization, the motor speed M1 and M4 should increase. M2 and M3 should decrease. Are you with me so far? And that is how you would do it. So now I'm going to take you to MATLAB and kind of show you where it can be done. So let me actually go ahead and new slide. So this is the assignment. Assignment is create a Mambo pendulum. So Mambo pendulum. So in your Mambo pendulum, what you will have is you will have this Mambo, and you will have a small string that is going through the center of the Mambo. So create Mambo pendulum. Implement complementary filter for roll and pitch. Third, find perform roll stabilization or pitch stabilization first. And step 4, roll stabilization. So what you should see, that if you have the Mambo pendulum flying, if you add, and you don't have to add the props, if you actually just rotate, you will see that motor speed should increase on the tilted side. So if it is tilted like this, these two motor speeds should increase, these two motor speeds should decrease. If you tilt it up, the back two motor speeds should increase, the front two motor speeds will decrease. This is just P control. It's not gonna be super duper accurate, because you will see actually that Mambo will continue to oscillate back down. That's totally fine, because in next step you would implement D, and then next step will implement I. So finally, once your PID controller is done, what you should be able to see is, if you have the Mambo pendulum, rotate, it will actually become stable. Rotate, it will become stable. And once you are comfortable, gradually you would increase the thrust, and then you will have that Mambo flying at the level flight. So that is what we are going to do, and you have 1 week. So it will be due next Thursday, so which is March 31st. This will be due March 31st. And I'm going to stop here and give you some hints about how to do it. So go to MATLAB and you can actually start this. And to be honest with you, this is all implemented. So you don't have to really look at this. If you look at the block, there is something called as the motor mixing block. It does all this mixing. So what you need to do is just send the PWM and it will change the delta W's. So any questions from online students or? Okay. So can you see, first, I want you to use these blocks, find the roll, then find the pitch, implement a complementary filter, and then once that complementary filter is done, can't see the blocks. Can you see the blocks now? Or just the MATLAB? Oh, okay. Oh, okay, okay. Yeah, okay. So what I need to do is new share whole screen. So now you should, are you able to see the blocks? Okay. So implement the complementary filter using the gyros and accelerometers, and first get it working. Once you get it working, then you want to go to the motor mixing block. So Yeah, you want to go to the motor mixing block and then change the PWMs or the speeds of the motors. So it's not letting me go into the motor mixing blocks. So first implement by Thursday, implement the complementary filter. And on Thursday, I would show you how you would implement this control logic with the motor mixing algorithm. So, and then we will try to deploy that on the hardware and actually do some test. With that, I'm going to stop here. And if you have any questions, I would be happy to answer. Yeah.
Currently the complementary filter is due tonight at midnight, not Thursday.
Oh, due today?
Yeah,
Okay, I'll make it due on Thursday.
okay, thank you.
So it's due Thursday.